If neutral atoms were simply neutral objects, then they wouldn't interact with the electromagnetic field at all. So the dominant interaction between atoms and light comes from the fact that they're actually made of components that are charged. And you get a major effect when you get those components and you separate them. So when they're all averaged over each other, of course, they have no net effect with an electric field. But when you apply an electric field, of course, those electrical charges tend to separate, and then you have a dipole. It's a dipole because they don't just freely fly away because they're strongly bound to each other. So you have a dipole on your electric field, and so your dominant interaction is the electric dipole. Now the electric dipole, we know the energy of it classically. It's just the dot product of the electric field with a dipole moment, and so for quantum mechanics it's just the same thing with hats on. Now we've already got the electric field operator in terms of our photon creation and annihilation operators. What's our dipole moment operator going to look like? If we have a dipole formed by a single electron being excited into a higher energy state, then what we have here effectively is a dipole moment that's got a charge of a single electron and the position of that particular electron. This is like a single electron atom model, except typically you have a complicated atom with a single extra valence electron that's creating the dipole moment. Now we recognize this very simply as a dipole moment. It's a charge times the displacement. On the other hand, it's a very bad basis for actually dealing with atoms. Because it takes considerable energy to change the state of an atom, a more natural basis for the atoms are actually the energy eigenstates, because they tend to be fairly well defined. Once you're in one, you tend to stay in one unless you get a large chunk of energy. So much so that sometimes we can describe atoms with just two levels. For example, you might have a coupling mechanism that's very resonant, and so it very particularly picks out two levels to couple, and all the rest are not affected. Anyhow, if we want to turn this Hamiltonian into the basis of the energy eigenstates, that's fairly simple. Where you know to have coefficients, this is a completely arbitrary operator in this some basis, some discrete basis labeled by the index k or the index j. And then I've got my electric field. Now another way of writing these dipole coefficients here is it's the inner product of the dipole operator itself with respect to the energy eigenstates, labeled by k and j in this case. Now those energy eigenstates have a particular symmetry. They must be either symmetric or antisymmetric. So if I take the inner product with respect to something that's antisymmetric in my coordinate r, then if I have the same thing in both its slots, so I have k and k, I definitely have to have 0 because the integral of any odd function is going to be odd. And it's only if I have a different thing in k and j that I have a chance of it being non-zero. And so therefore I know that the diagonal terms of this are 0. So if we're talking about a two-level atom, then my final Hamiltonian looks like. And furthermore, this coefficient here is just where I have the E and the G swapped over here, and so therefore it's just the Hermitian conjugate. And all of those things should have been vector valued. And we use the notation of these sigmas. Normally sigmas we use the Pauli matrices, but sometimes we use this notation. There's something a little bit surprising here. Here we have a transition from a ground state to an excited state, and here we have a transition from an excited state to a ground state. And we're taking the dot product with the electric field operator, and the electric field operator has annihilation operators for photons and creation operators for photons. Now what that means is that often you'll get the combination where you go from a ground state to an excited state, and you get rid of a photon. So that's the atom absorbing a photon. We'd expect that. And sometimes we'll get it where it goes from the excited state back down to the ground state, and it spits out a photon. We expect that process to happen as well. Much more surprising, you also have the cross terms. So these two things can happen. So you can have the atom get excited and you get an extra photon, which sounds like it doesn't conserve energy. And we have the opposite process, where you both lose a photon and have an atom de-excite, which also doesn't sound like it conserves energy. If we think about it a little more carefully, because we have the full range of possible energies of photons, even the terms where you lose a photon and excite an atom don't necessarily conserve energy. When you have atoms spitting out photons or absorbing photons, they can do it slightly off resonance. The reason that can work is that the energy of the system isn't fully defined by the energy of the atom and the energy of the light. The total energy of the system has to include the full Hamiltonian. In other words, it has to include the actual coupling term, and the coupling energy can be non-trivial. That said, terms in the interaction Hamiltonian that flagrantly disregard the energy conservation of the rest of the Hamiltonian are going to have less effect on average than terms that are more resonant. And that means we can make a very powerful approximation to this Hamiltonian. We do this in the interaction picture. And if we absorb the energy of the atoms and the energy of the photons, which is just this energy here, and if we absorb those into the operators, as we do in the interaction picture, then our resulting interaction Hamiltonian is going to be And we can see that when we pair up terms from the dipole moment with terms from the electric field, we're either going to get these rotations going in the opposite direction, or we're going to get these rotations going in the same direction. Now, if you have terms in the Hamiltonian that are rapidly changing sign, then when you integrate over any finite amount of time, they're going to have far less effect than terms that are making the state change in a more consistent direction. So instead of getting all four of these terms, we're actually going to ignore two of them. And this is called making the rotating a wave approximation. We're only going to keep the terms where the two rotations are counterpropagating. Where we've taken the dot products of the coefficients and boiled them down into just one function g, and we've also gone back into the Schrodinger picture. If we hadn't gone back to the Schrodinger picture, then we would have still had the differences in the rotations in these terms. And when we put the bare energies back, those differences in rotations go away. So what we did is we went into the interaction picture in order to notice which terms we could ignore. Then we went just back to our original picture. So in other words, we've come from here, said I'm going to ignore two of those terms, and we've ended up with this. And the rotating wave approximation is a very dependable, useful approximation to give us a nice, simple atom-light interaction Hamiltonian.